Okay, alcohols. Right, long story short, alcohols, so what's the difference between an hydrocarbon and an alcohol? You have an OH functional group on there, and critically, with an OH, if this is attaching to a carbon, I'm going to have lone pairs coming out of that oxygen, and if you don't include the lone pairs, you'll lose half a mark in each instance. Yes?
I don't know if I'm just making up things. Is the OH just a hydroxide though?
Hydroxyl.
Yeah.
Yeah. So, we'll cover that. The functional group is a group of atoms responsible for the reaction of a particular compound, and in the case of alcohols, and look at this, bad diagram, you have to have, you don't put your lone pairs on your structural formula, but you do put them on the structural diagram. Okay? And so methane, ethane is a hydrocarbon alkane. Methanol, ethanol is a hydrocarbon alcohol. Do you understand the difference?
Yeah.
They have the OL on the name. So instead of methane, ethane, propane, butane, pentane, it's methanol, ethanol, propanol, butanol, pentanol. So if someone says, what type of hydrocarbon is pentanol, you say it's an alcohol. It's not a methane, it's not an alkane, alkene or alkyne, it's an alcohol. So that's what the OH group defines. The functional group for alcohols is hydroxyl, a common alcohol is ethanol, methane, ethane, but there's the OH. Please note the structural formula. So there's the OH. So where is the OH? It's on the end of that last carbon. So you've got that CH3, CH2, OH. CH3, CH2, OH. Ethanol. Not particularly toxic, very important alcohol, used in beverages, perfumes, dyes, varnishes. So it has a variety of uses, and it's a very simple short chain alcohol. You'll notice, very importantly, ethane, ethene and ethyne at room temperature are gases, but ethanol at room temperature is liquid. So the addition of that single oxygen there, and for the love of Pete, do not do this, which I have seen too many times, where people say, there you go, she's right.
No, that's a HO.
But that's a double bond and a hydrogen.
No, but then you
and a single bond and an oxygen.
No, it doesn't work.
I mean, straight away, if you share my disgust, I can tell, and obviously I'd be deducting more than 1 mark for that. That would just send me into a blind rage. So, don't forget your lone pairs. Can I change? Yep. Yeah? Okay. So, is everyone clear? The functional group of the alcohols is the hydroxyl group. It's OH. You need to put, reading left to right, OH, say on the end. It can come in on the side. It can come in multiple locations for constitutional isomers in the same way that a methyl group can. But you need to have your lone pairs for the oxygen. The oxygen will always have lone pairs. Okay? Right. Now, this is key for the practical activity, so pay attention. We'll do the practical activity next week. Let's have a look at this. Now, you obviously know about conservation of matter. This idea, right? Chemical reactions, bonds are broken and new ones are formed. Atoms are neither created or destroyed. Look, CH4, 16 grams, 2 oxygens, 2 times that is 64 grams. And if you add this up on this side, it's exactly the same weight. What I'm saying to you is this. I've got methane gas. I'm burning it with oxygen. I've got the same number of carbons, the same number of oxygens, the same number of hydrogens on this side. It's a balanced chemical equation. If I start with 1 carbon, 4 hydrogens and 4 oxygens, and I finish with 1 carbon, 4 hydrogens and 4 oxygens, where's the energy coming from if nothing is created or destroyed? You must understand it's in the bonds. you understand, like I start with one carbon and I finish with one carbon. There's 4 hydrogen, there's 4 hydrogen. There's 4 oxygen, there's 4 oxygen. So where is that heat that I feel when I've got a campfire going coming from? And it's because this guy here, CH4,
Bonds breaking.
yeah, you're changing bonds. And this is oxygen, right? See, those bonds here and those bonds there have a lot of energy in them. And by breaking them, these are low energy products, low energy bonds in the products, and the difference is what you feel as heat coming out. So the energy here, these are reactants with high energy bonds. So you want to draw that. Reactants, high energy bonds. This is what you need to draw. These are products with low energy bonds. But we do not destroy atoms. We cannot create atoms. We can just break bonds and make bonds by setting up conditions. That's a key idea that you have to understand. Okay? Don't be thinking that, oh yeah, at the end of the day I've lost some carbons because I burned some wood in a fire. That doesn't happen. The carbons that started in the log have gone to carbon dioxide and they've gone to ash probably, but it's the exact same number of carbons. And the hydrogen and the oxygen that were in the wood have gone off to probably form water vapour. Okay? And then that will condense. Okay? So yes, when you burn things, you get water as a waste product. Who's seen the movie The Martian? Yeah, we'll have a look at that scene later on where he's sitting in a closed room. He's got about 150 litres of water in a tank because they just keep recycling it. They clean out whatever you urinate, they just scrub it off and get the H2 out and just keep filter, yeah? He's got about 150 litres of water. He needs about 600 litres of water in that room to grow his potatoes. He needs 600 litres. There's no getting around that mathematics. Okay? He needs to make water. What do? You burn rocket fuel. Carefully. Because any combustion reaction produces water as a waste product. That's a gimme. Okay? There's your water as a waste product right there. Okay? Does anyone have any questions about that? This is a key idea. It will be examined. Okay? You need to understand bonds being broken and reformed is where the energy comes from. So if you listen carefully to the crackling of the campfire, it's not stuff being destroyed, it's just bonds being broken and reformed. Okay, that's fundamentally what is happening. Okay, never the destruction of atoms. Okay, has everyone got that diagram down?
No.
So you don't even know what this energy scale is. You don't need to know. Just put a number there. That's 10. That's 0. This is high energy. This is low energy. And the difference here is heat coming out in a combustion reaction. That's what you feel on your hands. The heat generated is the bonds, is the difference between the high and low energy bonds. Okay. Now, I'll give you a moment or so to finish that. You notice the C for cram card is in the top right corner. A very, very important idea. Now, I might change. I'll erase my notes over here. Okay. And then we'll have a look at the next slide and we'll see something. Now, what have I told you about chain length? The longer the chain, look at the third point. On the sheet that I gave you, there was an additional piece of information I made you write down. The longer the chain, the higher the energy derived. Let's have a look at that. What does that mean in real life? This is methanol, right? Methanol, ethanol, butanol, and gasoline, which is probably 6, 7, or 8 carbon chains. Chloe, don't waste time. What's happening here? So methane is just a simple, or methanol is just an OH group attached like that. Now, methane 2 carbons with an OH group, and off you go.
Oh.
And
Oh.
hang on.
Very low.
I've got the battery pack. There we go.
Yeah, PowerPoint sounds out.
Oh.
Oh, there we go. All good. There's ethanol with 2 carbons. There's butanol with 3 carbons and an OH group, and off it goes. As you see, as the chain gets longer, now remember this is for the same volume of fuel, okay? So if it's a litre of methanol, ethanol and propanol, we've got the same amount of fuel, but the amount of energy from each of those increases as the chains get longer, you know? Well, how is that possible? It's hard to draw, but if that's,
More bonds to break.
well, if that's CH4, here's CH4, right? Here's CH4, these aren't connected, right? So we have 2 carbons, but they're not connected, CH4. Here's methanol, ethanol. Here's an equal volume of carbons, right? That's fewer hydrogens, but it's an equal amount of carbons, but that bond there is a higher energy bond. And that the presence of that bond there is why that ethanol, when you burn an equal volume, well, you don't even need to burn an equal volume. If you've just got energy that you're outputting, if I have a car with a litre of methanol in it and a car with a litre of ethanol in it, and you just run them, the car with the ethanol will go further. You'll get more energy out of the same volume of fuel. And then I've got another car with butanol, and I get more energy for the same volume of fuel. That's what's going on there, okay? Does anyone have any questions about that? That, again, is a key idea. The longer the chains are, the more energy you get out. Okay. Now, and the reason why, do you see a why question there? I won't get you to draw the structural diagram, but I've functionally done it for you there. The reason why that is because that particular bond in the carbon chain is a higher energy bond. Even though there are more bonds in these two in total, the hydrogen-carbon bonds are quite low in energy, but the carbon-carbon bonds are high in energy, and you can get a lot more out of them. Okay?
Yeah.